away we go. So today we're just doing 2 by 2 matrices, a 2 by 2. So 2 rows by 2 columns. Those are the only matrices you're going to be doing stuff with. But today is, and some of the days to come, are about finding inverses. So think of like, in Algebra 1, did we do that in Algebra 2? I think we did at the beginning of the year. The inverse property. Do you remember inverse property? What's an inverse? Like, what's the inverse of 2? Not that, okay, that's the opposite.
-1/2.
Just a positive 1/2. Inverse, right? The inverse of 2 is 1/2. If you multiply inverses together, you get 1, right? So 2 times 1/2 equals 1. So inverses are going to get you that 1 when you multiply. We're going to be doing something very similar to that. We're working with inverses, but now in a matrix type of setup. So the inverse matrix looks a little bit different than just 1, but I think you'll see like, oh yeah, that's totally an inverse. So first thing to talk about here, by the way, not all matrices will have inverses, but most 2 by 2s do, okay? Some won't, but most of them do when they're a 2 by 2. Okay, a square matrix is your number of rows equals the number of columns. So we're going to focus on the 2 by 2, right? That would be a square matrix. But it could also be a 3 by 3. We'll talk about those a little bit. It could be a 4 by 4. It could be a 5 by 5. But when your rows and columns are equal, it is a square matrix. A multiplicative identity is if I take a number and I multiply it by 1, I should get that number back, right? We talked about that idea back in, probably the first chapter. I don't remember what chapter that was. So when we have this multiplicative identity, this thing that gets us the same thing back, it always looks the same. It's just, it grows depending on what matrix you're working with. So a 2 by 2, that identity matrix is 1, 0, 0, 1. Okay. When it's a 3 by 3, that identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Do you see what's happening there? Where are the ones always? Ones are here. Ones are here, right? The ones are always the diagonal. I guess that's this way for you guys. Everything else is a 0 when it's the identity matrix, okay? So that's a multiplicative identity. When you multiply a number times 1, you get that number back. If you multiplied a matrix by one of those identities, you would get that same matrix back, okay? The reverse of that is saying if you take a matrix and you multiply it by its inverse, you should get those guys back, right? If I take a matrix and I multiply by its inverse, I should get my 1, which in this case is that 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? So it's like I was saying before, 1/2 times 2, those are inverses. Thank you, sir. So multiply those together and you get a 1 out of the deal, okay? Okay, so this first stuff, we're just verifying that matrices are inverses. What that means is we should be able to multiply these together. So this is a 2 by 2 times a 2 by 2. So we should be able to multiply them and get this as our answer. Then we know they are in fact inverses, okay? So let's do that. All we're gonna do is multiply that 2 by 2. So this is gonna be 2, 3, and 2, -1, right? First row, first column. I'm going to do a whole lot less highlighting right now because we've done a lot of this, right? So I feel like we don't need to highlight quite as much, but tell me to slow down if I lose you. So you would go 2 times 2 is 4, plus 3 times -1, so a -3, right? First row, first column. Second column would be 2, 3 with -3, 2. So it's 2 times -3, or -6. 3 times 2 is 6. Okay. Second row, first column is 1 times 2 plus 2 times negative 1. And then second column is negative 3 plus 4. Okay, simplify that. 4 plus negative 3 is 1. Negative 6 plus 6 is 0. 2 plus negative 2 is 0. Negative 3 plus 4 is 1. Is that an identity matrix? Yes. So you just verified that these two matrices are, in fact, inverses of each other. If you multiply them together, you should get the inverse, the identity matrix. Okay. Okay, so you try the next one. Multiply those together. Tell me if those are inverses. I'm going to do the work up here while you're doing the work there, and then you can check your work against mine. All right, so it should look like that, which gets us 1, 0, 0, 1. Are those two matrices inverses? They are. Okay, we got the identity matrix back, so that verifies that they are inverses. Any questions on that? Okay. The next thing then, there is this word called a determinant. What do you see in the word determinant? Determine, right? A determinant is used to determine if the matrix has an inverse. Okay, so if we can find a determinant, we can figure out, is there actually an inverse for this matrix? And like I said before, most 2x2s have an inverse, but not all 2x2s have an inverse. So we do always still need to just check. When we do this, okay, if our determinant of whatever matrix we have equals 0, then there is no inverse, okay? If the determinant of the matrix equals 0, there is no inverse. If it's anything else, so if it's anything but 0, then there is an inverse. Okay, so if you get a determinant of 17, there's an inverse. If you get a determinant of 36, there's an inverse. If you get a determinant of -7, there's an inverse. The only time there is no inverse is if your determinant equals 0. Okay? Okay. So here's how a determinant works. If you have the matrix A, that is A, B, C, D, okay? Your determinant is found, it kind of feels like cross-multiplying. It's not, but it feels just like it. These aren't proportions, right? But you do essentially the same thing, and it matters the order you do it in. So start in that first spot, top left. You're going to go A times D, so AD, and you're going to subtract and then go this way, B times C. Okay, that's how you find your determinant. You cross multiply, if you will, and subtract those numbers. Okay. Okay, so let's do this. We're going to find the determinant of these couple of matrices. Can I move on from that? Are we good there? Okay. So to find the determinant here, what am I multiplying first? -3 times -5. So that's a positive 15. And then subtract. It's always going to be subtraction. And then what am I multiplying? 4 times 2, which is 8. So 15 minus 8 is 7. So your determinant is 7. Does this have an inverse? Yes, this one has an inverse. Yeah, we'll find those inverses later. Okay, so look at letter B then. Multiply diagonal, you get negative 12. Subtract a negative 12. So negative 12 minus a negative 12 is 0. So your determinant is 0. Does this have an inverse? No inverse on this one. Okay? Okay, so finding the determinant is the simple part. What we do with the determinant gets a little more involved. So let me show you what this is going to look like. It says if you let A, your matrix A, be A, B, C, D, and the determinant of A does not equal 0, so any other real number, okay, your inverse will be, we're going to go here with it. Remember, inverse is that you raise it to the negative first power, okay? That's how we show the inverse of A. Maybe you want to write that. Okay, that's how we say this, inverse of A. So the inverse of A is going to equal 1 over the determinant of that matrix. And then here's what you do with the matrix we started with, okay? It's going to be, notice what we started with, A, B, C, D, right? It was this. You take your A and your D and you swap them. So now it's going to be D here and A down here. And you take your B and your C and you make them opposites. So whatever it was, the opposite of B goes here. The opposite of C goes there, okay? The way I like to think of it, you don't have to necessarily think of it this way, but I always think of it like this. 1 over the determinant of A, and then I just, in my head, I go swap these, change these. Okay, so you swap the first diagonal, you make opposite the other diagonal. Okay, this right here, or this, the determinant of A being divided, that's why you can't have a determinant of 0, right, and still get an inverse, because you can't divide by 0. So that's why 0 is the one that doesn't get us an inverse.
When you say make it opposite, do you mean like...
If it's positive, make it negative. If it's negative, make it positive.
You don't like, if it was 2, you don't make it 1/2, right? You don't...
No, you don't cut it in half. You just change the sign.
Got it.
Yeah, opposite of what it was. Okay, so here's what we're going to do. There are 3 of these problems, and then we're done. We are going to find the inverse of the matrix, okay? Now, maybe you want to just write off to the side the 2 steps that you're always going to do with this, okay? There are 2 steps to this process. Step 1 is you are going to find the determinant, okay? Step 2 is you are going to multiply you're going to set up your inverse equation, right? So you're going to do the 1 over the determinant of A times the swap and the opposite. Okay, so those are your 2 steps. Find the determinant first, then plug that determinant in down here and solve. Okay, you got to multiply that out. Okay, so step 1 on this first one is find the determinant. What is the determinant on this first one? What do you do first to find the determinant? -2 times -4, so 8. And then it's subtraction, right? 5 times 2 is 10. So your determinant is -2. Okay, so we found our determinant. Now we're going to go back to this setup and set that up, solve it, okay? So it's going to be step 2 here, 1 over what? What is our determinant? -2, okay? So it's 1 over -2. And now you take your matrix and we lay it out from what it was. So remember, these 2, we do what with? Swap them. So negative 4 up here, negative 2 down here. What do we do with these two? Make them opposite. So it's going to be a negative 2 and a negative 5. Okay, now think about what this is. I'm going to erase my little 2 here just so you can see what this, I want to put this out in front. This is the inverse of m, right? So the inverse of m equals a negative 1/2 times that matrix. Now you actually multiply it. Maybe we should put that as our third step, multiply. So you don't just stop right there, okay? You always want to simplify. So the inverse matrix, negative 1/2 of 4 is going to be a positive 2. Negative 1/2 of negative 2 is a positive 1. Negative 1/2 of negative 5 is a positive 5/2, or you could call it 2.5. I don't mind if you do that. And then negative 1/2 of negative 2 is another positive 1. So this is the inverse of m. Okay, so find the determinant, set it up in that equation of the inverse, and then multiply that out, and you're done. Yes, ma'am. You do, this is scalar multiplication, right? You take that negative 1/2 and you multiply it by all 4 things. Okay, letter B. What do you do first? Find the determinant. So the determinant of A here is what? 3 times 6, so 18, minus 9 times 2, which is 18, which is 0. What does that mean? It means you're done, right? If you get a 0, there is no inverse, and therefore you cannot find the inverse because there isn't one. So when you get 0 on these problems, everyone goes, yay, because you don't have to do any work. So we would say the inverse does not exist. Or you can just say no inverse is fine. Okay, last one. I'm going to have you try it. So remember your steps. Number 1, find the determinant. Number 2, plug it into that inverse formula and then actually multiply it out. Yeah.
So, like, what does the A and the M mean?
The matrix, right? Matrix A, right? This is matrix A that we're working with. So the inverse of A does not exist, right? If I say the determinant of A, I'm saying the determinant of this matrix.
Okay.
Does that make sense?
Yeah.
Okay. All right, give it a go. See what you get. Remember, you're going to start with the determinant of C as your first step. All right. Tell me what you got. What's this top left term? Negative 3. What was next to that? Negative 5. What's in the second row, first column? 1 and
2.
Good work, team. Okay, so here it goes. The determinant is going to be a negative 6. Oops, not plus, minus. Minus 1 times a negative 5 is a negative 5, right? So plus a positive. So you get a determinant of negative 1. Okay, that means then we are going to take 1 over our determinant. Okay, so your inverse is going to be 1 over negative 1. And then you're going to multiply that. Remember, swap those first diagonals. So 3 up here, negative 2 down here. And then change the sign. So negative 5 becomes a positive 5. Positive 1 becomes a negative 1. And now you multiply. So this is equal to negative 1, right? Negative 1 times 3 gets you negative 3. Negative 1 times 5 gets you negative 5. Negative 1 times negative 1 gets you positive 1. And -1 times -2 gets you +2. So this is your inverse. Good on that? Find the determinant, set it up in your determinant formula, multiply. You're multiplying by 1 over -1. Yeah. So it's that scalar multiplication. Everything gets multiplied by -1.